we have given today's title as Quantum Simulation from Concepts to Technology. And our layout of present day talk would be uh, starting from the cooling of atoms. We shall discuss the C phenomena. Then we shall see how the optical lattices can be developed, and then they can be used also to develop atomic mirrors and cavities. And then we talk about the scattering problems, and then some interferometry, which is being used uh, following these simple discussions. So when we want to talk about cooling atoms, so it simply means that we want to control their thermal motion, and by reducing the thermal motion, we we reduce the temperature of these particles. So how we can reduce their uh, thermal motion? The first step in doing so comes with the help of lasers. So we apply lasers, and uh, and basic phenomena is very simple. If we just start with that, whenever we were talking about the absorption of field and the atoms, so we were understanding in our previous discussion that the field is absorbed by the atom. Field is absorbed by the atom, and the atom um, well, whenever the field interacts with the atoms, atom absorb the radiation field, and depending upon the field frequency equivalent to the transition frequency, and in this the energy is transferred from the field to the atom. At the same time, a momentum of the photon is also transferred. So this is something which is we may say that conservation of energy and momentum in that sense. And just the opposite happens once the photon is emitted, because once the photon is emitted, so the radiation is radiation emission reduces the energy of the particle atom, and at the same time it gives a kick to the opposite side, that's recoil photon. So the recoil kick, so that the photon emission is now balanced. Photon emission in one direction is balanced by the recoil kick in the opposite direction. So that is how the momentum conservation is again going to take place. So this phenomena is very useful in performing the laser cooling phenomena, because in experimental setup, how we proceed, that um, we have our atoms, and these atoms are going to observe um, these these atoms are going to observe optical radiation field, and this radiation field is in the opposite direction from the direction of propagation. So, so what is thing which is associated now with the atom is that it is in motion. It moves, and we apply an optical field opposite to its direction, propagation. So, due to the motion of the particle, it sees, we have set the frequency of the field in such a way that the field frequency is smaller than the atomic transition frequency. And so once this atom moves following following the Doppler shift, so this field frequency is seen larger. So once it is becoming equivalent to the omega naught, it absorbs the field and gets a kick in the opposite direction through its propagation. So that reduces the velocity of the particle, because you're getting a momentum kick in the opposite direction. So that this process goes on many times. So this it creates a slowing down of the atom. So so we have another photon field photon field coming from the opposite direction. That is for any photon, any atom which is going in the opposite direction to this. So this way we are in a position to reduce the velocity of the particle once the interaction is happening over many times, and then this process reduces the temperature of the particles with up to millikelvin. beyond millikelvin, we further reduce the temperature by reducing the velocity of the particle following Sisyphus cooling phenomena. Now, this Sisyphus cooling phenomena is applied to the atoms in the presence of a gradient, polarization gradient of the field. So the word Sisyphus is connected to the Greek mythology, where there was a, a a person who was given punishment by the king at that time, that he had to uh, take a big stone, roll a big stone up to a hill. And the understanding was that by the time he reaches up the hill, the day finishes, his job is stopped, and the stone falls down. So before he reaches the top of the hill, the day finishes and the stone rolls down again. So next day he has to start the work again from the beginning. So this way, so this phenomena is seen at work uh, uh, in in cooling the atom further, and this uh, in this way the temperature is further reduced to 2 order of magnitudes. And finally, we have our evaporative cooling, which is standard the cooling of a teacup, tea in a cup. So the atoms with higher energies, they just evaporate, and the rest of the atom with lower energy stay in the track. So this way, we are in a position to cool the atoms up to microkelvin and to nanokelvin scale, so which is very, very small. So we cannot reach absolute zero, but we can come to smaller and smaller scale in this way. So using this particular approach, we are in a position to develop newer state of matter, which are named as the Bose-Einstein condensates. So in developing Bose-Einstein condensate, we have gone up to the temperature limit of nanokelvin. Now, a simple mathematics can connect our temperature concept with the thermal energy by this simple relationship, that we can write temperature as temperature dependent thermal energy as kBT, and it is now going to be related with a with a with a with a with the dynamics of the with the kinetic energy, average kinetic energy. Sorry. So this way we can connect thermal energy with the movement of average energy of the particle, E square average by 2m, and this helps us to calculate the de Broglie wavelength. And we notice that the de Broglie wavelength is inversely proportional to the square root of the temperature. So as the temperature lowers, the de Broglie wavelength of these atoms increases, and then we can have a simple relationship looking at some particular kind of atoms like rubidium atoms, and see that if we at room temperature, the de Broglie wavelength could be as small as 0.2 millimeter. This length scale is even smaller than the size of the atom. If we reduce the temperature of these atoms to 1 Kelvin, so the de Broglie wavelength is around 0.3 nanometer. So this is comparable to the size of the atom, because the rubidium atom is a big atom. So, but if we go further at lower temperature scales, which we want our atom to go by using these cooling mechanisms, so we see that at 10 raised to the minus 8 Kelvin or 100 microkelvin, we have the de Broglie wavelength as 3 micrometer. So now this micrometer de Broglie wavelength is comparable with optical wavelength, which we have around us. So this way, we can so going to the scale, going to this scale, we see the quantum mechanical properties of the atom going to take place, and also um, we can control the de Broglie wavelength of our system in this way. Okay, now yesterday we were also talking about the atom field interaction in the dispersive regime, and that was once we say dispersive regime, I remind or recall that the atom transition frequency is very far or very different from the field frequency. So that means that field cannot be absorbed by the atom and in this scenario. So, but we understood that the transition will not take place. If the electron is in the ground state, it will stay there. But uh, our atom will be observing a force because of this optical field present. And we can write the Hamiltonian in this simple way. The first term is describing the kinetic energy term, and the second term is talking about the potential energy term. This is what we attribute to the atom, and this U of R term is basically the spatial dependence of electromagnetic field. So that is very important. So now, if we want to calculate the force which is being applied by the optical field to the atom, that can be easily calculated, and we calculate that force as minus del V. V is the potential energy of the system. So from there we calculate we obtain a simple relationship, and we observe that this force is depending upon the field profile, how the field is appearing, and the change into the profile where the change is larger, we see the force is larger. And then we have this force depending upon detuning as well, detuning between the field frequency and the transition frequency. If the field frequency is very large, transition is small, so it's positive. And if field frequency is small, the transition is large, so it will be negative. So a positive or negative sign of delta will change the force from attractive to repulsive. So that's why we are in a position to make use of the field to attract the atoms or to repel the atom at the same time. So this is an interesting application. So now, if we move forward, so we observe that based on this simple understanding, we can make interesting, useful instruments like atomic tweezers, optical tweezers. So optical tweezers are again based on this phenomena that we develop the gradients of the field profile, and using the gradient of the field profile, we attract or repel particles. These particles can be living objects like bacteria, but it can be like anything like nanoparticles or atoms even. So then, using the same principle, we are in a position to develop Gaussian beams which can attract the atoms towards this center, thus making something like a waveguide. So the atoms which are moving in this Gaussian light beams attracted towards the center of the beam, they will be moving, taken away in this way. And it can be even nanoparticles or any other thing. So now these optical tweezers can be made in various different configurations. We can make them in single-ended or single beam optical tweezers, which are having a field gradient at one particular point. Field is focused at one particular point, and there we can have the maximum force acting on our specimen, if it's a living or non-living. We can make dual beam optical tweezers, so it's a finite size optical tweezers, which are having some profile which is changing with the position of the field. So now we can use this to attract or repel or any nanoparticles or particles in general. They can be even living objects like bacteria and DNA and so on. So in this sense, this optical tweezers is used in numerous ways. It can hold, it can apply force on some specimen, it can measure force, it can calculate the local viscosity, and holding and trapping atom is starting from here. So this was the first approach, this was first scheme which was provided in 1969 to hold or trap the atoms. After that, the cooling trapping field started at a very fast pace, and people were becoming more and more excited to develop numerous kind of traps. One of them is like Paul trap and many other traps. So for neutral particle, for ion, and even electrons. So now going further in this in our discussion, we can open another topic here that we were talking about optical field, which was applied in the opposite directions. So if we have, so this is another topic which we start up here, and we'll combine this with the previous topic soon. And so in short, before we start any discussion, the focus of our present discussion is that in how many ways we can develop the potential or optical gradients, because we see that optical gradients or optical profile change is useful to attract or repel matter. So in how many ways we can develop these kind of uh, fields as per our requirement. So one of them can be a standing wave field, for example, and that is the simplest, because if we have a laser beam and apply a mirror, so it will be interfering with the, so incoming field will be interfering with the reflected field, and we shall be seeing a standing wave. So this is the simplest profile which we come across almost very often in the laboratory. So it's a standing wave profile. If we have this arrangement little bit bigger in a plane, we use, instead of one mirror, we use two mirrors. So wherever they intersect, we shall see there will be a two-dimensional optical surface appearing, and that would be something like an X-ray in a plane. So this will be another possible optical surface or optical potential which can be developed using our two-dimensional configuration. We can take this two-dimensional configuration to three-dimension, and we can develop a new setup which is now obtained by interfering three lights. Rather, in principle, there are six lights. So here we have one laser beam coming towards the mirror, and one is going opposite to this. Here we have four such possibilities. One moving toward this mirror, then it is going in this direction, and then going this direction, and then this mirror is reflecting this all back, and so on. So we have, at this point, there are four beams intersecting with each other. And here we have six beams intersecting with each other, and so on. And their intersection makes at the intersection point something which is very interesting array of small optical potentials, which are spherical in shape. So this is something which is quite useful. We shall see how it is useful, because now if we let this kind of optical potentials or these kind of optical potential meet our atoms, which are very cold, so they will be seeing a newer kind of arrangement, because now we see the interaction of these cold atoms with these different kind of optical arrangements make something newer possibilities. And we see that these cold atoms appear in a one-dimensional optical uh, 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 optical uh, uh, optical surface in the form of disks. So they are confined in one direction, or direction of the field along the axis of the cavity, but the atoms in this condensate are free to move in x and y plane. If this is a z-axis, so in x and y they are free to move, and the confinement is only in the x direction. Here we see something, the confinement is in two dimension, and the atoms are in the condensator free to move in the vertical direction. So here we have something like atomic wires, and here we have something like quantum dots. So this is an interesting way to develop quantum dots, which are confined in three dimension. It's an atomic wire, and it is something like atomic disks, again using the simple arrangement. So this opens up a newer subject for us as well, because if you see carefully, here we are developing a three-dimensional atomic structure, which is very much similar to crystals. Because in crystals, we see atoms placed periodically away from each other. An electron can hop from one place to the other place, from one atom to the other atom. And here we see this optical crystal is made by atoms, and they are stored, they're confined in the optical balls, and these atoms can jump from one side to the other side. So now the scale is different, but the phenomena is the same, because now it is not electrons, but it will be atoms. In conventional crystal, we have electrons which hop from one side to the other side and then keep going. Here we have atoms, and atoms are periodically placed in a very uniform structure. It's a crystal structure. This can also be resembled with something like, if you remember, there is something like carbon tubes. The carbon tubes are made of carbons, but these tubes can be made of any material, which we can confine in this optical structure. It can be rubidium, it can be cesium, it can be anything like that. So this is very useful. So we have a toolbox in which we can pick anything of our choice and use as per purpose. Something very interesting, that we should have a feeling how big, what are the numbers behind this? And we can pick up the numbers by saying that at the center of this atomic ensemble, which makes this Bose-Einstein condensate or the atomic wires or atomic quantum dots, the density is 10 raised to the power 12 per cubic centimeter. Now this density is far smaller the density of air or density of molecules in the air. So in air, for example, we have a density of 10 raised to the 19 per cubic centimeter. So this makes it very interesting that we have these quantum wires, or we have these quantum dots made by atoms, but very, very light in the density. It's very less dense. So in that sense, we cannot compare with the conventional carbon wires, because carbon wires are really thick, if you remember. It's used in chemistry, in biology, in microscopy, in various ways. So this is first thing. And second thing is that this lattice depth in which we have confined these atoms, it is of 10 raised to minus 10 electron volt. So this number, this potential depth, is making the energy scale 10 order of magnitude higher than what we see in case of electron in a conventional crystal. So that means any phenomena which we are trying to perform in this optical crystal is 10 order of magnitude higher in energy. So that's an interesting thing, that we have an energy scale which is very high. So to perform any phenomena, we shall see which kind of phenomena we have in front of us, and we shall have a quick review of these kind of various phenomena coming soon. And one thing we discussed, that the de Broglie wavelength can be connected with the temperature. So we reduce the temperature, we increase the de Broglie wavelength. So de Broglie wavelength is useful for this optical system as well, because if the de Broglie wavelength is smaller than the optical wavelength, so we will not be able to see these coherence if attributed to the atoms. And if the de Broglie wavelength becomes comparable to the optical wavelength or becomes larger than the optical wavelength, then the atomic ensemble start presenting quantum mechanical properties and wave-like properties, and we would be able to see quantum mechanical effects emerging out. So this is something which is very interesting in this domain. So this comparison is useful in terms of the temperature as well. So we have to reduce the temperature to such a value that it should be comparable to the wavelength of the optical field. And this also makes uh, our standing wave in the form of an optical crystal. Because uh, okay, I shall come back. And now this optical potential which is being provided to the atoms can be made very shallow or very deep. So if the potential is presented to the atom is very deep, so the atoms would be staying at the lowest level, will be seeing only an harmonic oscillator, because the potential is so deep. But if the potential is shallow, so they will be appreciating the periodic nature of the optical field. So this is again a simple difference in the atomic behavior in different kind of optical lattices. Okay, now it is an interesting comment which is normally attributed to Feynman, that one thing which is very popular among the quantum computer people, they attribute statement like a quantum machine that can perform computation using quantum mechanical elements. It should be developed and to perform the quantum computer. The second thing which we normally observe as a quantum simulation, because what is message behind this statement is that you can develop a controllable quantum system to simulate any other quantum system. So we have some such quantum system or which is achievable or which is difficult to achievable based on our conventional present day technologies. So we try to develop the same setup at a very larger scale, and it has all the same characteristics as that of that small system. And that gives us a good space to study and use. So with this, we can also develop these optical lattices where we use atoms and as a prototype of our solid state crystal lattice. Because in solid state crystal lattice, we have atoms which are coming one after the other, and electron is hopping on them. So here we can develop one-dimensional optical lattice, which is having atoms in there. And the good thing is now these atoms can tunnel from site to site. And we can see, uh, uh, we can use this very much similar to what we see in our conventional case of um, uh, this material lattice. So here we can study the resistivity, we can study the tunneling effect, and so on and so forth at a very large scale. And we have again these quantum particle in our control, in our use. These quantum particles are made by atoms, and they are very, very heavy. They're very heavy as compared to an electron, but they have all the same characteristic as that of electron. Fine. So if we can even introduce charge up here, because if we replace neutral atom with ions, they have the same characteristic. They get spin, which was a question yesterday, and they also get uh, uh, a charge. So no problem. So in that sense, we are in a position to make a prototype with the help of cold atoms and optical fields. And the prototype is that of a conventional atomic structure or atomic crystal, or where we use electrons. Electron goes from atom to atom, site to site, and moves, and we see an electron current is propagating. Here we have atom which is able to tunnel from one site to another site, optical site to another optical site, and we see an atomic current going on. So this comparison makes an entire new subject, which is different from electronics and named as atomtronics, where we use atoms and optical lattices and make all the same instruments which we develop in electronics domain. So this is something which is interesting. And if we use that two-dimensional array, two-dimensional optical surface, which we were talking about, and we place atoms very in an ordered way, so we can develop these optical structures to develop various different studies. For example, we can use this kind of setup to study the Bose-Hubbard model, which is again very popular in semiconductor condensed matter physics. If these atoms are charged, they have spins that can be easily attributed, that can be easily made on an atom by, for example, adding an electron or taking an electron. Because adding an electron on a neutral atom will bring all the same characteristic that is attributed to the electron. It will get a spin, it will get a charge, it will become an ion then. So in the presence of ions, we can again have Fermi-Hubbard model, which can be used and studied in this system. And these systems are very popularly used to develop superconductivity, Mott insulator, and a phase transition in these systems. We can study further things like quantum revival, Barry phases, and Hall effect in these systems. So these topics in these kind of optical lattices are very well discussed in my book. So shortage of time is not letting me to discuss all of them here. But once you open, you can see they are having a very good detailed discussion on these topics. So now, in addition to these known presented things to you, we can develop more sophisticated optical surfaces which can be of further use as well. For example, if we have three laser lights which are in a plane and they have all polarization perpendicular to the surface, they can combine together and make triangles of these atoms, atomic triangles. Now, easily you can understand that here we are trying to develop more and more configurations which atoms may take in a real crystal. Fine. For example, it's an experimental setup, and it is possible to see a hexagon. It's named as Kagan lattice, and then we can see that we can make different kind of use of this. So this has hexagon symmetry. So here we can study something like graphene structures in our atomic using our atomic systems. So these things we can develop very often in our laboratory experiments and use them to develop prototype of our conventional solid state condensed matter physics systems. Other things which are very interesting, and we can easily say that now the duality is at work, and that is we can make more interesting configurations which are useful for various different applications. We shall see which kind of applications they are good for. But now if we use a nanofiber, if we use an optical fiber, and we pass two different kind of fields in here, which are two different decay lengths. So they combine together and make a potential in the radial direction. So now this potential is having a minima, and that minima is able to store atoms. If we have atoms placed around these optical fiber, they will all be trapped at the minima because there is a minimum of this potential. So now in the radial direction, these atoms will be trapped, but they will be taken along the fiber from one place to the other place. So this is an interesting surface trap, which is different from our conventional magneto-optic trap, which was previously used. I have not discussed that so far, but in our previous discussion, once we want to develop bosons and condensates, we normally use magneto-optic traps. But here we have a newer kind of trap, which is surface trap, and that can be obtained by simply an optical fiber and two fields which have different decay constants, one positive, the other negative. Oh, okay, two decay constants. So now this way we have this going on. And as I mentioned that now this optical fiber is having coal atoms around its surface. So this optical fiber is having another surface of coal atoms around around the optical fiber, which can be taken from one place to the other place. So this acts like a waveguide. So this optical surface trap is going to confine the atoms around the nanofiber, and since confinement is only in the radial direction, these atoms can be pushed along the axis of the fiber outside. So that means in this way we can take atoms from one place to another place, keeping their coherence, length and temperature maintained, because these atoms are not coming in contact with the fiber. Because if fiber surface is of room temperature, is at room temperature, so in between we have an optical surface coming where we have these atoms stored. Other thing which is very interesting in this domain is that we can use nanofiber of optical fibers, nano optical fibers, and these nano optical fibers have field, exponentially decaying field outside the fiber. This is, we know, uh, from the basic understanding of field propagation in an optical fiber, because if field propagates inside the fiber, so outside it decays exponentially. So this exponentially decaying field is seen in the radial direction in this form. It's an exponentially decaying field. And if this atom rotates around the optical fiber, it develops a centrifugal force. So this, an attractive force and a centrifugal force, which is throwing it outside, balance together and make a minimum of the potential. So wherever we have these two forces balanced, the atom would be trapped gain around the fiber. So it's another kind of trap which is there for the atoms. So this way, the advantage of this kind of trap or the previous kind of trap is that we have enormous space to work, because in magneto-optic trap we have 6 magnets coming in different 6 directions, and there is not enough space to see our sample, which is now trapped inside. But here we have enormous space to work. Okay, now fine. We discussed that if we can have various different possibilities for the atoms inside the field, and then we can make various different kind of configurations, and then we move on further and we change the setup entirely, use the optical fibers and field around them, and make newer traps, newer arrangements where we can again use our atoms. Okay, what happens if our field or if our atoms interact with the field for a short time? Field is not there forever. So now, in that sense, we have a newer question at hand, that we send an atomic beam. So the atoms are coming, they interact with the optical field placed in a cavity in the form of lasers in a standing wave field, we can say. And standing wave field is as simple as saying that a laser light is coming, and here we have a mirror, and a part of the light is reflected, the other is incoming, they interfere with each other, make a standing wave field. So if we have a standing wave field and an atom is coming, so how it will interact? What shall happen after the interaction? So one thing is, so this brings us to the discussion of scattering of atoms from the optical fields. Now, the duality is very interesting. Why I'm using the word duality? Because this optical surface, which is standing wave field, acts like a grating. You know grating in the optics, simple. So this acts like grating, and this atoms or beam of atom is now going to act like de Broglie wave. So this is a wave which is coming at grating, and now the scattering begins. So if the incident atomic de Broglie wave is perpendicular to the diffraction grating made by the atoms, made by the optical field, we shall simply see that there is a symmetric scattering. So the atomic beam will scatter, or atom will scatter after passing through this optical grating. But if the atomic beam meets the this grating at an angle, so then we see something we already know as Bragg diffraction. So Bragg diffraction is a property of light once it comes on a crystal. Fine. If the wavelength of the light is comparable to the atomic spacing, so the light will be reflected back, and we can have various different applications of this um, Bragg scattering. So here we have this de Broglie wavelength, and this is now competing with the wavelength of the standing wave field. So here we see that there are two possibilities after the scattering, that it may go straight or may reflect, it reflect following the Bragg scattering phenomena. So now, so this, in the real experiments, this work is reported, and we see this profile probability distribution of atoms after interacting with this optical field. And we have this symmetric behavior both sides around the origin. And this keeps on going, spreading as the time evolves. And in case of Bragg scattering, something different. Okay, wait. Now, if we let these atoms pass through various different kind of, if we let these atoms pass through all possible grating elements, so then we have something which is named as a Talbot effect. And here we let these atoms pass through all these possible openings or the grating elements. If you remember the diffraction grating, so this is having various different elements or various different apertures from where the light may pass. Fine. So if you let these, if the atoms are passing through all these different diffraction grating elements, so then they will interfere with each other, and we shall be observing the image of the diffraction grating at a certain distance, which is named as the Talbot length. So at a certain length, we shall see that the diffraction grating is having its image. Now, something is very important to note. If we are doing this experiment with light, and we are using a diffraction grating as we do in our college experiments, and with the diffraction grating in our hand and using it in front of the sunlight, we can easily see that on a paper, the image of the diffraction grating comes. If we just set the distance between the grating and the paper. Fine. If we just remove the sunlight or remove the grating, so this disappears. But here we are working with the atoms. And here we are having the diffraction grating, which is made by the optical field, which is standing wave field. So now we are depositing material on our screen. So if we, so the image of the grating is permanent. So whenever we close this experiment, so we lose nothing, because the so the grating image is now seen on our film, so on our detector screen. So this is a permanent image in that sense. Okay, so this is used in various different ways. So this behavior is seen in the non-relativistic domain, and in the relativistic domain, we have this interference picture appearing and so on. If we work in the Bragg scattering domain, so then we shall see that it's possible for the atoms to opt for undeflected path or a deflected path. So there are only these two possibilities for the atoms after the Bragg diffraction. So this is seen again in the experimental setup. And what we can see, the probability of finding the atoms in undeflected and deflected paths can be calculated, and we see this sinusoidal behavior. So as the time evolves, we see that the probabilities of going from deflected to undeflected can be reversed as well, depending upon the time direction. Now, this particular scattering is very useful in making interferometers. Now, this is a Mach-Sender interferometer, which is obtained with the help of atoms. So we have atoms which are having a optical surface or optical diffraction grating right here, and then they perform the Bragg scattering, and we apply again another diffraction grating for another time of interaction. Pi is only the time of interaction, and pi by 2 is half of that particular time. So this helps to make us a diffraction grating based interferometer. It's named as Mach-Sender interferometer. This interferometer is used very often in various different interferometry experiments. In developing sensors and devices based on atoms, we see this effect this interferometer is used very often. For example, we see, which are very popular today, as gravitometer, which are based on this Mach-Sender interferometer, or there are these measurement of G and so on. Well, so we shall discuss those devices as well, which are based on these Mach-Sender interferometer, and okay, this thing is sometimes named as the amplitude interferometer because it divides the amplitude of the field in this and this two directions. We also have something which is named as the phase interferometer, and this phase interferometer is coming once we use an atomic mirror and let the atoms fall on this, and they jump and change the phase, and then they meet again at this point, and we can see how much the change is there. So this particular arrangement can be made in this simple experiments or setup where we see the bouncing atoms. Earlier, I was showing the atoms which are coming and interacting with the standing wave field and performing Bragg deflection. So that was one simple approach. And then here I'm saying that we have cold atoms which are coming under gravity, and they are observing an exponentially decaying surface, and that exponentially decaying surface is providing a mirror scenario. So the atoms come down, meet the optical surface, which are going to provide a mirror for these atoms, and then they keep on bouncing. And after one bounce, they meet again, and we see there is a change in the pace of this. We may come back to this in a little more detail tomorrow. So we can leave this discussion for tomorrow as well. So nothing to worry. So here I conclude, and I simply say that tomorrow we're going to talk about atomic control for quantum engineering. We shall discuss gravitational cavities, atomic trampoline. We shall also talk about some surface probe microscopy, and then we shall see how we can develop atomic wires and quantum circuitries. So here I thank you. So if there are any questions, so you can ask. Thank you.
Thank you, sir. Thank you so much. Okay, if you have any question, please feel free to ask from sir. And yes, introduce yourself first to sir. Yes, Larry.
Sir, I have a question, a very basic question regarding the Kulingo pattern. Okay, could you please explain about the Kulingo pattern? Does it mean the shifting of electrons from the high energy level to the lower energy level?
According to which atoms? Could you repeat your question?
Okay, the Kulingo pattern, the count of Kulingo pattern, does it include the shifting of electrons from the high energy level to the lower energy level?
Okay, when we want to cool the atoms,
yes,
we want to restrict their motion. So if we connect it with our conventional everyday discussion, so we say that we see that if we have higher temperatures, so the dust particle in air, they move faster. They have high thermal energy. If we reduce their thermal energy, they will be they will be cold. Or in other words, if the temperature lowers down, so their movement compared to each other would be lesser and lesser. So actually, we want to find ways or mechanisms in by which we can reduce their movement, average movement, average process.
You have explained about the uniform pattern by the light. Is it possible, because from the basic level, we have already learned about, or we studied about that the interaction of any atom or the electron with the light, the electron gets excited and shift from the low energy level to higher energy level. So how it would be possible to, you can say, minimize the thermal energy or control the motion of the electron by the light?
Well, that I was trying to explain on the first slide.
Yeah.
And that I was saying that now you have to introduce or include the movement of the atom. Because once the atom is moving itself, so any optical field which is coming towards it will have a Doppler shift. So we make arrangement of the experiment in such a way that means we set the field frequencies in such a way that they contribute under the Doppler shift. So that is the key thing. So of this one. So you are very much correct. The phenomena is the same. That once the atom is absorbing field, so it is going to absorb or gain energy and kick. It's a kick to the atom. And once the atom is releasing the photon, so energy is slowed down, it gets it recoiled. So if the photon is going in that direction, in the right direction, so you get it recoiling in the left direction. It's just a bullet from a gun. You fire the bullet, and the gun goes in the opposite direction.
Okay, thank you. Anybody else? Okay, the one from. Please first introduce yourself to sir. Okay, Aslan.
And hello, I'm a research assistant there. Actually, I did my bachelor's in physics from Pakistan Institute of Engineering and Applied Science. Yeah. I have some questions. First of all, can we able to cool atoms with the one-dimensional beam? Like not all the case atoms are moving towards the beam or away, like or blue shifted or red shifted. So, like, can we cool the atoms with one-dimensional beam up to the B side?
Well, in real experiments, you have a puff of atoms. You have a cloud of atoms, and that cloud of atom is a three-dimensional arrangement. So if you provide only one-dimensional field, you can get the cooling, but only along one axis, because they are free to move in all other directions. So that would not be efficient cooling. So this is something which is making the experimentalists to develop. Pardon?
We can achieve millikelvin, right?
Well, it's not the matter of kelvins, because it's only one axis
Right.
which is being in which you are providing cooling phenomena. So you may say that you have restricted the motion along one direction, but they are free to move in any other direction. So that is not cooling.
We can confine them with the magnetic field, like in that direction, right?
Well, you have, if you talk about magneto-optic trap, so you use them together. There's magnetic minima, magnetic potential, you develop the magnetic minima, and then you have optical trap and optical forces. And optical forces are very important.
The question is that can we cool alkyl atoms only? Rubidium, as you talk about rubidium, belongs to that family of rubidium and cesium. Can we only cool these atoms or any other component of the family?
So far we are more comfortable with these atoms.
The one is that we talk about ions in the atomic lattices. There's a Fermi-Hubbard model, if I'm not wrong. So I have talked about, does this still follow the Bose-Einstein statistics? Like when we talk about ions in the atomic lattices, because something Fermi happens there.
For me, Hubbard model is going to use fermions,
Yeah.
the spin particles. Now, using Pauli exclusion principle, you cannot have more than one fermion in one level. So this is by definition different from condensation. Because once you talk about Bose-Einstein condensate, you say that in one level, you have placed all the atoms. So you say all the bosons are now placed in one state. So that is our condensation. But once we work with fermions, we have to think differently. So now we are not worried about one level. Rather, we are more worried about their distribution over all the levels. That is now coming into the discussion.
Okay, you have? Yes, introduced, yes. First one.
मैं क्लास से मैंने एक सवाल करना है कि अगर मुझे कोई कंडेंसमेंट फिजिक्स से कोई जैसे ग्राफीन कोई स्ट्रक्चर है उसे मैं सिमुलेट करना उसके अंदर ट्रैप के अंदर तो क्योंकि डेंसिटी तो काफ़ी कम है तो उसकी जो बात प्रॉपर्टीज अगर मुझे स्टडी करनी पड़े जैसे इलेक्ट्रिकल कंडक्टिविटी तो क्या चेंज होगी डेंसिटी की वजह से कम डेंसिटी की वजह से
Density of what?
जो मैं एटम लेटेस्ट बनाऊंगा ऑप्टिकल लेटेस्ट के अंदर वहाँ पे ग्राफीन का स्ट्रक्चर बनाऊंगा.
You see, if you're talking about the density of atoms at the optical sites,
Yes.
that is less. That you're talking about. Okay, but these cloud of atoms, which have the probably wavelength bigger enough that they collectively behave. So these atoms are still far, far heavier than an electron. So you simulate, as you're saying, you simulate that particular crystal in your craft using atoms at a very, very high scale, at a very high energy scale, as I mentioned to you. So that would not be, that would not be making any problem with the density.
क्या उसके अलग प्रॉपर्टीज जो डिफरेंट प्रॉपर्टीज होगी ये कंडक्टिविटी डिस्ट्रीब्यूटिव वो चेंज होगी उसके अंदर.
Well, you see, those would be on a newer, higher scales. Because if you work with electron, which is very, very small particle, as compared to an atom, and you look at the resistivity or conductivity of that electron, and now this cloud of atoms. So there is a far easier approach with the atoms. But even though they have lesser density,
Okay,
The good thing is that they are in the same state. They are coherent, they are in the same state, so they move collectively. That's key.
So, sir, what is the role of detuning here? Because while we are shining light, it doesn't matter while we shining on resonance or off resonance, because due to Doppler shift, it will automatically off resonance from that light. So, thus we have to explicitly mention or
You talked about the two beams in the opposite direction. Well, okay, now if you see carefully, the arrangement of the frequencies is that omega is less than omega naught. So now, if one frequency is becoming comparable to the transition frequency because of the Doppler shift. So the opposite, if the light photon or light field is coming in the same direction, they would be having the opposite effect. So the difference between these two frequencies will become even larger. So there will not be any transition in that direction.
okay, thank you. Anybody have a question? Anybody else? Yes, please. Please first introduce yourself. to-
Sorry, my name is Imran. So, how we control the frequency, the field frequency?
Okay, well, if you want to talk about the field frequency, you have to pick up another laser field. So this is because you set your experiment right in the beginning, that which kind of laser you're using for which kind of atoms and what you want to do with these atoms. So you have a very clear discussion, a very clear experiment in your hand. if you want to have a waveguide, for example, which is based on the attractive field, so you set all these parameters in advance and make your waveguide. If you want to talk about developing atomic mirror, for example, which is now going to reflect the atoms. If any incoming atom will reach this exponentially decaying field, and they will be observing an exponentially increasing field in the opposite direction. So you make this all in the beginning, that you are developing atomic mirror.
Okay, thank you. Anyone else have a question? Okay, let me ask from a virtual participants. And this question is by the Mr. Sadiq, and he is asking how field frequency is controlled.
It's the same question which was asked by Javed.
Okay. So, Mr. Sadiq, your question is repetitive, so Sal already answered the question. Okay, the next question that is by the Shahzeeb Arif, and he is asking, is superconductivity not harmful?
Um, well, it's a characteristics which we observe. So it is very much decided about our use, which we want to use it. So
Okay.
far, there is no value of that.
Okay, the one question that is by the Ikra Gulzar, and she's asking, I have one question. What are the biggest source of noise or error in measuring tiny optical forces on individual atoms?
Okay. It's a very interesting question because the noise sources are there, and they can be thermal photons which are available, or they can be we can say that these are the thermal photons which we may find as introducing some kind of noise or error.
Okay, the one question that is by the Abubakar Sadiq, and he's asking, we are making an artificial lattices to have control over it. Is there some way to control natural materials, or what are the advantages to build lattices artificially over naturally occurring lattices?
Okay, let me repeat your question. So you're saying we are making artificial lattices to have a control.
Yeah.
If is there some way to control natural material?
Or
Fine.
what are the advantages then?
If you want to control natural material, you can, but you have to really decide what you want to do. If you want to have an ideal material with no impurity in here, so then you have to really increase the cost of your crystal by and removing the impurities. So that is possible. It's going to make it. And you say what are advantages?
Yes, what are the advantages to build lattices artificially or naturally?
Well, here I tried to present it in the form of quantum simulation, that we are in a position to make larger, bigger scale systems to observe the same effect or phenomena which we see in the smaller systems. So this is a big advantage.
Okay.
We have not to use very expensive detectors or.
Okay, Farman Aziz Shinwari, I will ask your question in the last question answer session, so please be online. Okay, the next question that is by Hashim Farooq, and he's asking, can we slow down spin rotational motion of atoms?
Well, that is again possible. There are very good experiments with the atoms and molecules where we really want to control their rotational dynamics.
Okay, sir, I request you please if you read the question that is by Farman Aziz Shinwari.
Okay.
And he's asking the slide optical forces on atoms mentions a lattice depth of about. How does this
shallow potential effect atomic tunneling
correct
and the simulation of solid state system in optical lattices?
Yes.
Okay. This particular information is for comparison. That if we have our atom optical systems. So the lattice depth is 10⁻⁻10. So if we see this in comparison with the conventional solid state crystal, so there this number goes down to 10⁻⁻19. So there is an around 10 order of magnitude difference in the potential depth. So that
Okay.
is huge.
Okay, the next second question, in the same slide, the de Broglie wavelength lambda become comparable to optical wavelength at ultra cool temperatures. What physical changes occur at this point? How does it indicate the onset of quantum degeneracy?
This is the first thing, that once you have your de Broglie wavelength becoming comparable with the optical wavelength, so you start observing the quantum mechanical effects, and you have the coherence length, which is the same for all the atoms.
Okay.
So this is
Okay, thank you so much, sir.